Hi, I'm Kayla Muse, and today we're here to talk about polymers. So what is a polymer exactly? So polymers are large molecules that are consisting of long chains of atoms that are covalently bonded together. They're also called macromolecules due to their large size. Monomers are the small molecules being used to synthesize the large polymeric chain. There could be a polymer of the same monomer as shown in the pictures, they're all dark circles, or they could be different. So some examples of a polymer would be natural polymers or synthetic. So for natural, an example would include wood, wool, starch, rubber, skin or hair, and for synthetic, nylon, polyethylene, polypropylene, polyvinyl chloride, and polyester. There are 60,000 known synthetic polymers out there, and we're going to cover 6 major ones that are of interest. So how are they made? So there's 2 different ways that I'll talk about. The first one is addition reactions. The linkage of N molecules of ethylene combining to form the polymer polyethylene. So the monomers being used are simply being added to the growing chain, and the products consist of all the atoms of the starting material. So in the end, no other products are being formed at this time. We represent it with an N because it could be such a large number that we wouldn't be able to write it out. It would just be a waste of our time. So a closer look at this. So as you can see, we have a free radical that's appeared in our equation. This unpaired electron is highly reactive, so that's why it's being introduced. It's going to attach to the left side of the ethyl group of our monomer, and this is going to cause breaking and forming of our bonds. So this double bond in the middle here is going to change to be a single bond. One electron is going to move to the end to connect with our free radical, making a single bond, while our other electron is going to move to the end to make another free radical, as you can see right here. This is going to create the cycle to continue. As you can see here, we found a new monomer, and then these are going to form in the same way as these did. The electrons are going to move, and this double bond is going to break, and we're going to have a free radical at the end. So linear versus branch. So first of all, I just want to talk about intermolecular forces holding polyethylene together, and these are known as dispersion forces. So these are the attractions between molecules that result from a distortion of electron cloud, causing an uneven distribution of negative charge. So as you may have seen in the textbook and in our videos, there's a necking example, and this is when a plastic bag is being stretched. Molecules are unevenly distributed throughout the bag. So now back to linear versus branched. We'll start with branched. This was the first to be manufactured, and it's a good example of produce bags found in the supermarkets. So they tend to be stretchy and transparent and not very strong, and this is due to their branched structure. Molecules are spread out unevenly, and this irregular branching is causing for more movement of the molecules. It's called low density polyethylene due to the molecules being so spread out. So now we'll go to linear, and it's also called high density polyethylene. And this consists of long chains and that are parallel to one another. So due to its orderly fashion, this molecule is much more stronger, rigid, and it has a higher density because the molecules are so close to one another. This would be used to make toys, containers, and pipes, things that are going to need to have more strength. So the big 6 I brought up earlier, these are the 6 synthetic polymers that are most common. Each polymer is considered to be a thermoplastic, which means that with heat, they can be melted and reshaped over and over again. Variation in strength and toughness is dependent on their rearrangement. So as you can see here, the 3 polymers are very similar to the polyethylene ones that I talked about previously. The only difference is the change in their functional groups, and this changes their functions and how they're arranged. So most are head-to-tail arrangements, but there's also head-to-head, and there's a random arrangement of monomers which would impact flexibility of the polymer. The next way a polymer is made is a condensation polymer. This is the process in which monomers join by eliminating a small molecule such as water, as you can see here. So this is how polyethylene terephthalate is made, which is also in the big 6 group. So it's containing two monomers, and as you can see on the slides, we have ethylene glycol and terephthalic acid. They each have compounds that are going to join to make H2O. The glycol has H atoms, and this one will have OH. So they will combine to make H2O, and the remaining portions are going to join together, as you can see here, and they will be joined together by an ester functional group. And it's involving two monomers, and then so we're going to be getting two different water molecules. So next we're going to be on the topic of biodegradable polymers and what they are. So polymers, they are polymers that degrade as a result of the action of microorganisms and enzymes creating harmless substances that are returned back into the environment. So the whole end goal is to make the environment better in some way and change the polymers that we know into something that's going to help the environment. The rate of this depends on the molecular architecture of the polymer. So meaning it's correlated with the type of repetitive unit, morphology, hydrophilicity, surface area, and additives on the molecule. So it's all dependent on the time of the molecule, how long is it going to degrade for, and how is it going to impact the environment. So in the end, the polymers of high molecular weight are being degraded to lower molecular weight. They're going into smaller molecules. The potential of biodegradable polymers has been recognized for a long time, since they could be a way to overcome the limitation of petrochemical resources for the future. Fossil fuels could be partially replaced with green agricultural resources, as we'll talk about. Also reducing CO2 emissions, which we have seen in previous chapters that it is causing a change in global warming and having an impact. But as of right now, they haven't been able to fully replace the plastic materials that we use due to their high costs that it is. So the breakdown of this. So in some cases, biodegradation is not so simple. If we're dealing with an inert polymer, modifications need to be done in order to speed up this process. So a biopolymer may be used like starch, which I'll talk about a little bit later, and this would be mixed with polyethylene. This will just speed up the process of degradation and kind of allow us to move quicker. So there's three methods I'll talk about that are classified as biodegradation. So first, microbial action is when biopolymers are broken down by micromolecules, and these are to be discarded in landfills and soil. Photodegradation is action from the sunlight. Polymers are attacked photochemically and broken down to smaller molecules, usually being used in disposable mulches and crop frost cover. Mechanisms of degradation. So there's two different types. So there's enzymatic degradation, and this is when enzymes are used to break down the substrates. The substrate moves to the enzyme, and once these two are combined, they form the enzyme substrate complex, and then they are releasing new products, often including carbon dioxide and water. This process is generally used in the breakdown of proteins inside the body, heavily studied in biology courses. Hydrolysis degradation is the reaction in which water is being added to break down a molecule. Also seen in biology courses, the water cleaves the polymer, which leads to the formation of the monomers, which is the end goal, breaking down our large polymers into smaller ones. So the types of biodegradable polymers, we also have natural and synthetic. So natural proteins, polysaccharides, lipids, all inside the body. Natural would lead to inside the body kind of ingredients, I guess. Synthetic polymers would be polylactic acid and PCl, which we'll talk about a little bit later. So what can change? So with traditional plastic being made from petroleum products, this has had a negative impact. These products are also raising health concerns because if they're heated to a certain temperature, chemicals are being released into our bodies, which is having harm. So the solution is biocompostable plastics being made from biodegradable cornstarch. So as you can see here, I have one of the containers here. And in this case, starch is being converted into a polymer having a plastic-like feel but different chemical makeup as normal. This is known as PLA, polylactic acid, and it's being made from cornstarch, which is a common use for making these biodegradable polymers. This material has a positive impact on the environment and is being used all around us and promoting positive environmental awareness. So I found this in the cafeteria at our school. I also sell it at work at Sobeys. So as you can see, it is all around us, and it is being promoted more and helping us kind of realize that we need to change. So thank you.